This lesson is looking at linear correlation and specifically looking at scatter plots in Excel. So when we're looking at linear correlation, we're comparing two variables and how they are related. So I've got several examples here where we've got groups of a variable which we could call x and groups which a variable we could call y. So we've got one that's temperature volume, we have one that's pressure volume, we have one that's concentration and pH. So if we look at these values, we might notice some trends looking at them, but it's a little easier if we see them on a graph. So we are going to take these into Excel. So I've just copied and pasted them right into Excel. And actually, let's keep it so you can see most of Excel here. And with this, when we're looking to draw a graph of these, make a graph of these in Excel, right, we can select all of the data and choose Insert, and the kind of plot we want here is a scatter plot. So we put a scatter plot in here. Excel automatically does some defaults as far as where it puts it. But we generally want to add some things onto here, like a chart title, some axes. So in this case, whoops, didn't mean to move the title, I just want to change the title. So our Y title would be volume in liters, and our X title would be temperature in Celsius. Often on these, we will label them as Y, whatever the Y is, versus X. So in this case, it would be volume versus temperature. But I'm not going to be too picky about a title as long as you have some sort of title that makes sense, explaining what this is of. Another thing that Excel can do for us is we can add things like trend lines. So this looks pretty linear. We might pick add a linear trend line. And we can do things like display the equation and r squared on the chart. We'll talk a little bit later about what r squared means and also about what this equation means. So for now, it's good to know that we can do that, right? That we can say what this is and draw ourselves a nice line. So with these three questions, I would suggest you do attempt to make yourself some graphs to make sure you know how to do this. For the other two, I'm just showing you what the graphs end up being. But again, you can plug these in and try them. And with that regression line, that trend line, you'll notice there's a bunch of different things we can choose to put in there. And depending on which one we put, how well it actually matches what we end up having. You can see that line moving as I choose the different types of trend line. So we can get some pretty good trend lines. We could also, I thought we'd add more than one trend line, maybe not. So we can look at some different sorts of trend lines and what these things mean. Sometimes though we get a result that looks something like this, which doesn't seem to have much more relation than splashing paint on our diagram would. So if you look at those, they all give us some kind of sense of, do we have a relation, even if it's not exactly what that relation is. So your textbook gives a few examples here. If we have a nice perfect straight line up or down, we say we have perfect correlation. If the slope is going up, we say it's positive. If the slope is going down, we say it's negative. If we get something like that, that's usually a theoretical value. Reality doesn't very often work out perfectly. Reality often looks more like this, where we have, we can see a definite trend, but they're not all on one particular line. And here's a fairly strong trend. Here we've got a trend, but it's a lot weaker, both positive and negative. Here's that example similar to the one we had where there was pretty much, looks like a splatter painting. But we can also have trends when we look at them as I mentioned with that pressure and volume one, that might not be linear. So we may see some other trend going on in them. So something to watch out for when we're looking at those diagrams and what they tell us. So the diagrams are one part, but it doesn't really tell us how much they're related. So that R squared that we had showing on that linear equation actually comes from something called the linear coefficient, and it's calculated like this, which is kind of a big, scary looking calculation, but it's not as bad as it looks for a couple reasons. So if we look at that, those summation symbols we've seen before, so this time we've got sums of x's and sums of y. Be careful when you have sum of x squared with the squared inside the brackets, that says we're squaring first, whereas if we have the square outside the bracket, that means we are taking the sum first and then squaring the result. So if we were to do a calculation like this, the results that we get, again, tell us something about that correlation. So if we get 1 or -1, that's telling us we have that perfect correlation, negative being negative correlation and positive being positive correlation, right, where everything touches that line. But if it's close to -1 or close to +1, it tells us we have strong correlation. The closer it is, the stronger it is. So if we were given a set of data like you have in your notes, and you have a bunch of calculations there, getting those values, you can see I've got them in there. Well, where did I get them all from? Because that's a lot of repeated calculations. Well, repeated calculations, we know, are well done in Excel. So if we look at these calculations, I'm just going to highlight what they are, right? XY, multiply our x's times our y's. X squared, again, we take that power 2. Y squared, we take that power 2. So this is something we need to do over and over again. We know on Excel we can scroll down and add those up. Right, so we also needed those sums. So once we have them all in there, right, we can take the sum of each and again get one sum. You can scroll over, get them all. So although that's kind of a lot of calculations, they're repetitive and we can get Excel to do them for us. So plugging those into our formula is a little tricky. You do have to be careful. Again, I would suggest you pause and see, can you get these into your calculator like this? So this one, we end up with an R equals 0.954. That's telling us we have a strong positive correlation. If you go back up to those diagrams, right, we were given some values in there, right? So anything from 0.7 to just below 1, we'd say is a strong correlation. 0.3 to 0.7 is weak. Less than 0.3, right, then we're getting into that very, very weak correlation. So on that graph, when I showed it, actually, let's quick go back to that graph of the straight line. You'll notice it says R squared. So that R that they have there is actually the same R we're talking about, but here it's squared. So when we have R squared, we're actually talking about the percent of explained variation. So that R squared in the volume versus temperature one I showed a moment ago was 0.8519. So that says 85.2% approximately can be explained. In this case, where we have R is 0.957, if we square that, we get 0.951, and that tells us approximately 91.5% of the variation can be explained by these variables here. So in this case, it's the number of passengers versus the cost. So that's quite a lot of the variation in cost that can be explained that way. So obviously there's going to be other factors like the price of fuel and things like that that are going to vary. So not 100% would be explained by the number of passengers. It makes sense. So we'll stop there before we do a little bit more in the next video regarding linear correlation.